research is sort of multidisciplinary and takes a little bit of pieces from history, archaeology, geology, geochemistry, and I want to get into a little bit of a background so you have a better framework to understand the talk. North America and the United States and Canada, like we've all been talking about today, it's been dated to about 7,000 to 9,000 years ago. To people in this room, that's not a big surprise, but to people outside of this room that aren't into this stuff, it's pretty surprising. So literally thousands of copper artifacts have been found, maybe tens of thousands. These have been found mainly in the Michigan Copper District area, in the Isle Royale area and the surrounding Lake Superior region. As a consequence, there's thousands of copper mines found in the area that are the sources of these copper artifacts. So here are some pictures of the copper artifacts. You can see that the mines, you typically find these rock hammers in the mines, which this laser pointer barely works. This is from Delaware Mine. On the bottom left-hand side, I took a picture of those. Based on this artifactual evidence, there's been three major traditions of copperworking found in the United States, the earliest of which is known as the Old Copper Complex. This is dated to about 9,000 to 5,000 years ago. The Hopewell are identified a little bit south. The gray area is basically the extent of these copper artifacts and other artifacts like lithics associated with these traditions. The Hopewell existed about 2,000 years ago, and they were focused in the Ohio River Valley Midwest part of the United States. The Mississippian tradition occurred about 1,000 years ago, and it was centered in the southeastern portion of the state at sites like Cahokia, Spira, Oklahoma, Moundville, Alabama, where copper artifacts have been found. So almost nothing is known about ancient copper mining in North America. So my work, which I'm going to show you how I did it today, was to document the timing, the magnitude, and the spatial pattern, the location of the copper mining, basically to infer the mining activity, because lake sediments record environmental changes. So why this work is important? Because stuff like this garbage, has contaminated the public's understanding of ancient copper mining in North America. I have no problem with science fiction, but the problem lies where this stuff goes around parading as science when it's science fiction. And it's misleading a young generation of thinkers and potentially undermining the true and even greater mysteries of the ancient copper people. For example, I went to, right here's me, here's the great leader of the episode American Unearthed. He went to this mine and basically more or less said that this was an ancient copper mine. This was dated to the 1870s. So you mean to tell me he missed this sign at the entrance of that mine? Or is he just lying to get ratings? So using lakes, we can actually, can we measure the impact of prehistoric mining and what were the timing, the location of such impacts? And then, so how can we use this stuff to inform our understanding of ancient societies that did the copper mining? So I use lakes like this one, Copper Falls Lake. It's located, here's an aerial shot. It's located kind of south of Eagle Harbor. It's situated by these veins of copper that were mined both historically and prehistorically, as documented in Mike Forgrave's excellent work at the coppercountryexplorer.com, which I would recommend everyone take a look at who's interested in this stuff. So, of course, everyone knows this, but here's the study area we're going to focus on, the Keweenaw, Isle Royale, and the Lake Superior region. We have, here's a closer up shot with a little scale. These are great places to study this kind of work, to pursue this sort of work, because there's copper mining and it contains lakes. So the earliest written records of copper in this area came from Jacques Cartier's second voyage in 1535 to 1536 AD. He notes that the people in the St. Lawrence area have copper. 1610 AD, Samuel de Champlain met with Native Americans on the St. Lawrence River who traded copper with them. They said according to the record, they got this copper from a large river draining into a large lake. Subsequently, Native Americans guided Europeans to float masses of copper, like the one Don Spawn's sitting on here, the large one. But there is no written record of copper mining or active copper mining of the bedrock in the early contact period. Native Americans actually guided some European explorers to this famous boulder known as the Ontonagon Copper Boulder. So in 1667, the sensationalist Claude de Blonde, Jesuit, confirms the existence of this copper boulder in the Ontonagon River. In 1766, with the guidance of the Ojibwa, Alexander Henry the Elder sees the boulder and confirms its purity. In 1820, Henry Schoolcraft visits the boulder. 1841, Douglas Houghton reports copper to the Michigan legislature. And then in 1843, the Ojibwa relinquished their lands in the Michigan Copper District, and then the Ontonagon boulder was then removed by Julius Eldred. In 1847, Samuel Hill publishes the first map indicating the location of ancient copper mines near the Northwest Copper Mine. In 1850, John Foster and Josiah Whitney excavate that ancient copper mine and confirm that they were indeed produced by humans. In 1862, Charles Whittlesey publishes the map of the ancient mine pits on the Keweenaw Peninsula, which is on the cover of our little flyer. And here's a picture of it. In 1863, Whittlesey publishes minimum tree ring age estimates for the mining remains, basically counting rings on tree stumps that are located on top of the ancient mines. And Albert Hagar does the same thing in 1865, followed by several researchers in the late 19th and early 20th century. These together confirm that these mines were indeed abandoned for hundreds of years prior to the contact with the European period, probably but at least by 1200 to 1500 AD. So that's a minimum age estimate, so it happened before that. So radiocarbon dating established the temporal context of copper use in the Lake Superior area. In 1954, the inventor of radiocarbon dating, Willard Libby, revealed dates, measured charcoal from Encanto Cemetery, which had a lot of copper buried with people. He revealed dates that went back to 6,400, 8,400 year BP. When I say year BP, that means years before present. Present's defined as 1950, and these are all calibrated radiocarbon ages, the median of the calibration distribution. It's important when you're presenting radiocarbon dates that you make this clear, because radiocarbon years are different than calibrated years, or than calendar years. In 1965, Crane and Griffin dated charcoal from a copper mine pits on Minong Ridge, and they were dated about 4,000 to 5,000 years ago, which is, I'm going to use that interchangeably with year BP, just to switch it up. In 1992, Buchan's et al. Dated a piece of wooden string from copper artifacts using AMS, which is a new form of radiocarbon dating. He read that artifact to be 6,800 years old, and that was from the South Fowl Lake site in Minnesota. This is still considered the oldest reliable date of copper in the United States and Canada. In 1993, Susan Martin published dates of charcoal associated with copper artifact on the Keweenaw Peninsula at 20 KE20. One of the dates is 9,000 years old. And then in 2001, Thomas Pledger, who's speaking tomorrow, published 5 AMS dates from Encanto that range from 8,400 to 5,600 years ago. So the Portage Lake volcanic bedrock is the primary copper-bearing bedrock in the area, and you can see this in the orange here. It's dated to the Middle Proterozoic, as Bill Rose was saying, which is about 1.1 billion years ago. And it was part of the failed mid-continental rift. So I took the Charles Whittlesey map and imported it into a software known as GIS. And then I projected that, or geo-referenced that map to the orange, showed places where the Portage Lake volcanic bedrock is exposed at the surface, not covered with surface deposits, because this is these would be the regions that would be the most accessible to the ancient copper miners for actually accessing the bedrock and finding veins at the surface and such. So here's that map again, and here's kind of like we zoomed out. So you can see here is the Keweenaw down here on the right. Notice I also have Isle Royal here, which has a lot of exposed Portage Lake volcanic bedrock. This explains why there's also mines in that area today. So that was a little bit of the background. I'm going to get more into my actual research here. So why did I use lakes to investigate metalworking? Because previous research has shown that pollution that's emitted in the environment is recorded in lake sediments. This primarily has its origins in Claire Patterson's work in 1965, where he showed that the modern environment had higher levels of lead in it than natural environments. Lee and Tallis in 1973 showed that this 20th century pollution was recorded in lake sediment in Britain. With the advent of radiocarbon dating and other radioactive nuclides that you can use for dating, like lead-210, the changes in pollution were then extended back in time prior to the historical period, or modern period. 5, Joseph Graney developed this technique where if you use weak acid, and you dry the sediment, and you actually apply the weak acid, you can remove particulates, heavy metals that are actually stuck to the surface of the sediment. So you can isolate the pollution signal from the sediment. You're taking it away. You're not measuring the mineral component. You're not measuring the organic debris. You're actually measuring electrostatically bound cations that are in the sediment. So paleolimnology you may not be familiar with, so I want to get into it a little bit. This is a schematic of a typical lake you'd find in Michigan. So lakes are transient features on the landscape. They're formed, they fill in. That's how they work. So here's an early lake at the top. The sediments eventually fill in the lake till you get something like this at the bottom. The sediments are derived from biological and chemical production in the lake water, in the watershed or catchment, and that includes airborne particulates that are falling in the lake. These sediments therefore contain the signature of the environment that's around them. And human and natural causes can change this, the environment, and then they're therefore recorded in the signature of the sediment, chemical and biological signature of the sediment. So they're very sensitive indicators of environmental change. So here's a picture of the field team going onto the lake. You can see my advisor, Mark Abbott, in the green. We build like a little platform on 2 boats. We go out with basically a hand-driven coring system. We anchor the boat in the middle of the lake, and we extract cores going down the sediment deposit through time. And I'm going to get more into this technique so you guys understand it. Here's me on Isle Royal with a surface core from one of the lakes. So just this tube. You can see the layers of sediment here, and this is the sediment-water interface. So here's where the water column begins and the sediment starts, or the water column ends and the sediment starts. So here's a picture of a typical lake core from a lake, the sediment core. So at the top, is younger sediment. Then as you go through time down to the bottom, it's older sediment. So what we do is we take macrofossils, like little sticks, charcoal, pine needles, and we radiocarbon date them. So these are shown as these black dots right here with associated error. This top is kind of a side note, but it's lead-210. It's just another way of dating the sediment, but you can only use it back 100 years. So we take these dates in chronological order down the core, and then we fit this thing called a line through it. The line is the mathematical relationship between the depth on the y and the age of the sediment on the x-axis. So when we go down the core, all we do is put the depth into the equation for the line, and then it transfers it into an age. So we get the age of the sediment layer. So this is very important to understand when we're going to go ahead in this work. So again, here's the idea. This is how lake coring works. So here's the sediment layers. We take a core, comes back out, and that's what you got. So I'm going to focus on using on lead. Something didn't come up there. As a proxy for metalworking, even though we're looking at copper, for a number of reasons. I also explored copper and potassium. I used lead as a proxy, or like something we measured in the sediment, to infer copper mining activity because it's a toxic metal. It has a low melting point. It's found as basically a impurity in the copper, and it doesn't cycle readily in the environment, and it's very stable. So once it goes in the sediment, sticks to the sediment, and goes and settles, and it stays there, and it's relatively stable. So it's at very low concentrations, around 1 to 2 parts per million. So very small amounts of lead added to the lake are detectable. What this says, and I don't know why it's not coming up, only about 10% of the lead in the atmosphere today can be attributed to natural processes. The rest of it, 90% of it, is attributed to human-induced causes. So before the advent of human contaminants in the environment, lead cycling in the environment was very, very low. But some of the natural sources of lead include dust like loess, volcanic emanations, etc. So we assume that in the absence of humans, if we're talking about a lake on the Keweenaw Peninsula, the majority of the lead delivered to the lake is from weathering bedrock and soils in the watershed. And it turns out this input is remarkably stable over the Holocene. It barely moves. So you got a lake here showing, the sources of sediment with the arrows, where they're coming from. So what happens is when a human comes along, here this guy with a little fork, he's altering the landscape, and he's burning fires and working metals. He's emitting cations around them. You can't see it, but they're just flying all over. When you have a fire, basically you're creating a low pressure system. It's just shooting cations up above you. And as Larry and Buck mentioned, when you're working copper, it's putting powder everywhere. So this alters the environment around you. So here's a reconstruction of a copper mine pit that I think is pretty accurate. I think I took this from the Milwaukee Public Museum. You got to remember, these people were moving copper from a very hard bedrock. Sometimes these masses were several tons. You just have to picture the amount of manpower, soil disturbance, tree loss, the amount of fires, etc., that went into creating the copper mines you find today. And it basically becomes pretty intuitive that it must have affected the environment in some way. What I want to show you here is that using lake sediments they're a new window outside of the artifact record in which to interpret the human prehistory of the United States and Canada. And they inform our understanding of the natural baseline conditions of ecosystems. It's a long-term perspective, so it has implications for today. So some of you may be wondering what an ancient copper mine looks like. Well, a lot of you in the room may have likely seen them, but other people, not this crowd, it's a little bit more rare for them to see a copper mine. So here's a field team on an exposure to the Portage Lake volcanic bedrock. Here's the picture of a copper vein that Bill Rose, I think, showed earlier. I took it from his website. So this is one still in place at Washington Island. Here's a picture of what that looks like after the copper miners actually exploit that copper vein. This is near Delaware Mine today. I took this picture a couple of years ago doing field work up here. So they're basically following the strike of the vein, taking out the rock around it, going down. They can be sometimes up to 60 feet deep. These are pictures of the rock hammers that came from this pit. This is near Delaware Mine on the Trap Range in the Keweenaw Peninsula. And sometimes it look like this. Here's my hand next to a copper mine on the bottom right from Isle Royal. So this is sometimes, they found masses like this in these pits. This is one from Minong Ridge. This was 5,720 pounds. And across the entire surface shows evidence of being worked by prehistoric people. In fact, this is the description on the right. You can read it of how they described it. This was one of many pieces of copper that were found similar to this size on both the Keweenaw and Isle Royal. So Charles Whittlesley in the 1860s actually drew a cross-section of the pits he excavated. And you could see in the M right here is a copper mass, a very large piece of copper that was being hoisted or basically wedged out of the pit using logs. And then it was eventually abandoned as being deemed too laborious to be removed from the actual pit. And this is looking down the strike of the vein. So this is similar to that picture I just showed you a second ago. Sometimes ladders were found in these pits. So Minong Ridge is one of the largest documented prehistoric mine areas in North America and in this region. So I want to kind of focus my first part of this talk using the lake sediments on in this region. So we took a sediment core from McCargo Cove, which you can see in that black dot right there. It drains basically Minong Ridge here, which is the location of the ancient copper mines. So they're basically draining into this cove. Alfred Lane, this is kind of, I don't know, bled out or something. But Alfred Lane published a map, I believe in the 1870s, where he indicated that there were pits on this ridge, and I walked it myself, and I can attest to the impressiveness and the vastness of the pits on this ridge. They probably extended 1 or 2 miles from the western shoreline of McCargo Cove, almost continuously along Minong Ridge. Get into the chemistry. So again, I don't know why this is so dark, or why this is so light. Whatever. It's kind of hard to read. But on the y-axis is concentration. On the x-axis is time. So this is really unfortunate. You can't even see this. But anyway, so going up is more pollution. Going down is less. And so you could see here there's a rise. You can barely see it, but there's a rise in copper and lead. And that begins in the 1870s. That coincides with mining on the pit, on the Minong Ridge. As you go back in time, it stays stable until you get another rise about 5,000 years ago, 5,000 to 6,000 years ago. So this, when you take this and you look at the other metals, you don't see that distinct rise. You only see it in lead, copper, and potassium, even though titanium, magnesium, and iron are the most common metals actually in the bedrock. There's a lot of magnesium in basalt. So when you compare the titanium, magnesium, iron, and organic matter, which is at the bottom, this is kind of another proxy for just biological activity in the lake. And then you compare them with lead, copper, magnesium, and potassium, you see that there's clusters, 3 distinct clusters. The black being the natural or background levels. And then during 2 periods, there's this excursion to higher levels of lead, copper, potassium. One during the modern period, which is in blue, and then another period I call the old copper period, that's in orange. And you could see that it's similar magnitude in some ways to what happened in the modern period. So I interpret this to be the result of the copper mining in the area. And based on radiocarbon dates, it puts it between 5,400 and 6,500 years ago. So to account for the processes that affect metals in lakes, it's a very complicated story, but I'm trying to go quickly because we're kind of we're going a little longer than planned. We ratio the lead to reference metals, some metals that represent natural processes that are happening in the lake, because we want to account for natural variability. These reference proxies, like I was saying, are titanium, magnesium, iron, and organic matter. We put these into things called enrichment factor ratios. So we want to see how much the lead is enriched above the natural level. So when you read this, it says EF, 0 to 1 is about natural, and then like a 10 EF would be 10 times the enrichment factor of natural levels. These reference metals were chosen because they occur in high concentration in the bedrock, and then therefore should reflect the processes, just like I was saying, in weathering and other things like redox conditions. And the organic matter serves as absorption sites for the metals, so places for metals to stick in the sediment. For simplicity's sake, I'm just going to focus on lead because I don't want to overwhelm you. There's enough wiggles in paleolimnology to boggle your mind, and it's a lot to take in. So enrichment factors also make lead records comparable to other lakes because we account for site-specific average differences. So each lake is a little bit different. So we want to account for those differences because each lake has a different size watershed, different depth, there's different rocks around it, et cetera, et cetera. So we're going to look at McCargo Cove, that record I showed you with the big spike, and we're going to compare it to another lake, Chicken Bone Lake, to the south, because Chicken Bone Lake the watershed of the lake doesn't contain any ancient copper mines. So it should serve as a control site to compare with McCargo Cove, which we know a lot of copper mines exist around that lake. We can see if there's a difference. So here's the comparison down here. You can actually see this graph better. Here's McCargo Cove and the dot right here. Here's Chicken Bone Lake. We don't see this spike. This is consistent with the archaeology. There's no mines around the lake. So this suggests that what happened in McCargo Cove was indeed a local phenomenon, and it's probably consistent with the copper mining at the area. And notice the dates again on the x-axis and the time. Very, very, very long time ago. Yes, Don?
What about a spike 10,000 years ago on the bottom chart?
Yeah, that's a very good point. If you look, it's kind of misleading. It doesn't really get above 5, and the error is still below 0. So we consider that just still not a very significant rise. But if you look at, that's probably related to the deglacial sediment sequence. So as the glaciers are, I have that in gray here, as the glaciers are eroding, they're basically putting all kinds of stuff in the lake. So then the lakes become like true, what we would consider a lake in the Holocene after that. So this is consistent with what we know about the watersheds and the archaeology. When we compare McCargo Cove to radiocarbon dates of copper artifacts, we can see that there is a general agreement between the timing of that spike here. So we're looking at this is in BC AD, years before present, and radiocarbon dates the median ages of them from several sites in the area. And this is an archaeological timeline. So we can see that Renshaw site and at least 2 dates from Minong Ridge mine pits seem to coincide with that spike. This is more evidence that this is indeed a human-induced change at this lake. You also see some correspondence with Encanto Cemetery, which is another copper. There's a lot of copper at this site found in association with burials. But you're probably wondering, well, Dave, these 3 dates here don't seem to coincide with that spike. So I propose in my papers that these dates, because they come from the charcoal at the bottom of the copper mine pits, mark the infill of the pits after they were abandoned, rather than being reflective of the active copper mining period. So, Minong Ridge is only one spot in the area. So I want to shift gears and let's look back at the Keweenaw Peninsula, because I have a lot more lake records from that area. I have 5 lakes, the transect of the Trap Range along the northern part of the peninsula. So I want to bring up this map again. So the orange places are where the Portage Lake volcanic bedrock's exposed at the surface. The underlying map is the Whittlesley map. These little red dots are ancient mines. And so I have here labeled my 5 lakes. So this is the basis of how I chose these lakes, because they're located near ancient mines and along exposed places of the bedrock. We have Boston Lake near Hancock, Seneca, Copper Falls Lake, Lake Medora, and Lake Manganese. So here I'm applying the same methods I did at McCargo Cove. I don't want to get into that again. We cored small inland lakes this time instead of the cove, and we dated them with radiocarbon. These are maps of their watersheds. They're very small lakes. Lake Medora up by Copper Harbor is probably the biggest of the lakes by surface area. Copper Falls is one I'm going to focus on a little bit more. It has no stream going into it or a stream coming out of it. So all the water that enters a lake is through precipitation, and it leaves through evaporation. It's an extra simple lake, and it's an ideal site for this kind of study. The other lakes do have inflows and outflows and bigger catchments, which make them a little bit more difficult. But like I'll show you, they still do seem to record ancient copper mining. So what else do I want to say? Yeah, here's another map at the bottom left. You can see again the locations of these lakes. They're along this elevated ridge. You can see. So we'll move on. So quickly, I used 27 radiocarbon dates. These are those things called the age model that relates the sediment depth to the radiocarbon age. Here are the results. So it's a lot to look at, a lot to take in, so I'm not going to overwhelm you. And you might be thinking, maybe there's something else going on here. Because I always get this when I talk to geologists. What if it's something else? Without even giving me a suggestion of what else it could be. What if it's not humans? What if it's not humans? What if it's like loss, droughts, volcanoes, meteorites, something that's putting lead into the atmosphere? I want to say that these processes are not supported by my data. I don't show all this stuff. There's a lot in my dissertation. This is basically my dissertation. So I measured things called lead-stable isotopes. This is a way to fingerprint where the lead's coming from. The lead-stable isotopes in the sediment indicate that the lead came from the copper bedrock. So this suggests it's not meteorites, volcanoes, or loess, if I'm assuming they're going to be a different isotopic composition, which I think is a safe enough assumption to make because these lead in other concentrations like potassium increase at different times at each lake, even though they might be just 10 kilometers apart. If it was a meteorite or volcano or a drought, you would think it would occur the same time at each lake, or roughly around then. Since it doesn't, this rules out lusts, droughts, and everything else. So only the human impact is consistent with the data. As a test of lake sensitivity to lead pollution, I just blew up the last 500 years. So we have 1450 AD, around the time Columbus shows up, 1492, and we're going to the present. So you start to see an increase around 1750 that corresponds with lead metalworking, but in French colonial times in the Midwest, they're basically making musket balls with the galena deposits in the area. This continues to rise in the 1850s as copper mining takes hold. Smelters open up in the 1880s. We peak in copper production in this area in the 1920s. Then we, boom, hit tetraleaded gasoline, which puts a lot of lead in the air. So then that peaks with in about the 1950s and 1960s. With the removal of leaded gasoline and the closure of the copper mining industries and other smelters in the region, you then see a decrease. So this shows you that the lakes are recording both the timing and the magnitude of human activities in the area, reliably, both the timing and the magnitude. So we can be confident, maybe, that if we go back through time, they're going to be doing the same thing. Also note how stable the background levels are. And remember the tree ring data. It suggests that the copper mines were not active in the centuries leading up to European contact. This is both consistent with the historic record and what we know in the archaeology. So we go back through time. I'm going to just blow back up to, on the left-hand side, it goes back to 10,500 years ago. These are the two sites from Isle Royal. Here are the sites from the Keweenaw. Notice you see these anomalies at each site, McCargo Cove being the biggest. That seemed to occur more or less before 5,000 years ago, back to about 9,300 years ago. Since these are on a comparable scale, so they're all on from 0 to 20, because you remember I talked about enrichment factors make the lake records comparable between each other, and they're taken from a known Latin long location, we can actually put these into a computer software. So, because they have this thing called an XYZ coordinate, the Z being the amount of enrichment of the lake. So I use this concept to then produce maps of where you see the lead enrichment factor. So we're actually going to get a glimpse into how the mining activity shifted across the peninsula. And you guys in this room will be, outside of my committee and people that are in my defense, the first people to actually see these maps in the public. These are, if you're familiar with ArcGIS, I'm not going to kind of bore you with all this other stuff, but I preconditioned the data a little bit, and I clipped it just to the elevated ridge on the Keweenaw Peninsula where I have coverage. So using this approach, I found 4 distinct phases of copper mining activity. Phase 1 I call from 9,600 years to 8,400 years before present. And that's here. We're going to focus only on the Keweenaw records because there isn't much spatial coverage on Isle Royal. There's only 2 sites. It's a big island. So we're going to actually look at these maps right now. So there's a blank map. Red's going to be more pollution. Blue is just natural levels. Oh, there we go. Perfect. Thank you very much. That's why I got a tech guy on the staff all the time. All right, so here we go. I don't want to keep everyone late. I'm trying to keep this going quick and let's get pumped up. All right, so this can be the world's most exciting animation you will ever see. So here we go. So we're at 9,070 years ago. This is before any detectable spikes at any of my sites. 9,600 years ago, you see the first enrichment factor increase at manganese. This is Copper Falls Lake. This is Seneca Lake. This is Boston Lake. It doesn't really matter about the lakes, just remember the time and the area. That's phase 1. So that is, I think you can interpret this, I'm going to talk about this, but that's the mining shifting through time. So this is phase 2. It's a shorter period, only 300 years, 8,100 to 7,900 years before present. So there it is. Again, you see this pattern over and over again. It starts at manganese near Copper Harbor and Portage Lake. Down. These are 2 excellent natural ports. It always shifts, then it typically shifts to Copper Falls, which is near Eagle Harbor. Then we have phase 3 of the 4 phases. This is another 300-year period. And then the last period, this is the one that's typically associated with the old copper complex that is characterized by the Encanto Cemetery and Osceola and such. So the implications from this suggest that ancient copper mining is detectable in lake sediments in this region. And these prehistoric emissions appear to be lower than detected using this method other places in the world. This has been done in China and South America. This is the first study that's applied this kind of approach in the Keweenaw Peninsula or in the Michigan Copper District area. I want to note, this is for the archaeologists, metalworking pollution in North America appeared to occur before the regional emergence of agriculture. This is very unique in the world. And unlike the places like Europe, Asia, South America, where these other studies have been conducted. This has, I think, huge social implications. The timing and the location of these patterns could be related to inherent uncertainties in the radiocarbon dating, because there's always error. How much so, I don't really know. It's only going to be improved with more lake sediment studies, more radiocarbon dates. So don't think of these maps as static. They're living. They're going to be revised probably if I ever get funding, which is never going to happen, but through time. So just keep that in mind. But I want to suggest to you that these patterns are probably related to how the ancient copper miners sought out and exploited copper deposits. They're a window, a new insight outside of the artifacts into the ancient copper industry in North America. Brand new window. And these, for example, confirmed in the historic record. For example, numerous accounts from Copper Falls Lake note, this is up by Delaware Central Cliff Mine, note the extensive ancient copper remains. Whittlesey documented these on the northern side of the Trap Range. They're in these A's. See these little small depressions? He states that, you can also see here's the shafts. So they're quite shallower than the actual historic shafts. So here's an example of one of the shafts. Excuse me?
You can't tell what you're talking about.
Oh, sorry. So here's the cross-section of, oh, you can't see it. Here's a cross-section of the copper rock near Copper Falls. This is the Copper Falls Mine Company. So you're seeing the stratigraphic layers of the rock here. These are the shafts driven into the rock. This is, these A's represent these tiny little depressions on the surface of the rock. But they ended up being about 10 to 20 feet deep. That Whittlesey noted that they, as being ancient copper mines. So there's 1, 2, 3, 4, and then Copper Falls Lake is right back here. So I just kind of threw in a picture of one of those shafts, like what you're seeing right here. Here's the shaft going into the rock. This is kind of a side thing. Here it is here. So around Copper Falls Lake, which you can see here in the blue, and then also documented by Mike Forgrave, is these brown lines. These are the fissure veins. The pits in this area occupy a total length of several miles. They were 2 to 5 feet deep, 5 to 10 feet broad, some of them being up to 5 to 18 feet deep with a diameter of 20 to 120 feet for several miles. And they're also found at the other veins. So he's referring to this vein right here. Can you see the pointer? This vein right here. This is confirmed in the geochemical record. So there's Copper Falls, where I just was talking about. Notice there's a total period of 900 years of enrichment factor increases in lead detected at Copper Falls Lake. And here are all the periods where I detected. So it suggests that those remains took almost 900 years to make. And they happened at very distinct intervals, suggesting it wasn't done by one particular group of people. It actually seems to have happened different time periods. So Boston Lake only records one period the entire time, this southern lake. It's centered at 9,200 years ago. It doesn't record those increases that we find at Copper Falls Lake. This is really strange to me. This suggests that these mine pits, see here, documented by Whittlesley and near Boston Lake, those might have been some of the earliest pits in the area. Go ahead.
Just a quick point. Boston Lake's not a lake, it's a dam.
Okay.
It was built in 1900 or 1880 or something, but it's a dam, it's not a lake. So it wasn't there before 1880 or 18, it was just a little creek.
Well, there's about 5 meters of sediment in it. There's about 5 meters of sediment in that lake.
It was used to discharge the tailings, part of the tailings went in there.
Yeah, the tailings I remember seeing, but the radiocarbon dating is in order, and there's several dates, and there's accumulated sediment. It suggests that it might have been a smaller lake, but it was definitely persistent. It's on the older maps, such as indicated by Whittlesley and I think some of the other people.
Well, there could have been a lake there, but I mean, what we call Boston.
Right,
Pond
I understand.
is a man-made lake or pond.
It's man-made today, but thousands of years ago, it may have been a real lake.
Yeah, I have no way to, I think you're right. I do remember seeing the tailings, and it's definitely modified. Almost all the lakes, except for maybe, basically all these lakes have been messed with a little bit because there's been such a history.
Major archaeological sites have been found on Deer Lake, which is underneath the Deer Lake Basin now, in the basin.
Thanks. Well, I would say my data suggests that there was a lake there before. It was probably different looking and smaller, but there is a sediment record that seems to be there that's preserved. Basically, the only point I'm trying to make with this site, though, is that it seems to only record an early increase in pollution. This could potentially be tested with further archaeological data, and it shows that these pits, documented by Whittlesley, weren't just one people that just showed up in mind. It happened at different periods. It's very variable. It's more complex than somebody like Ancient America History Channel is going to let you figure out. They're just going to distract you for ratings. So another interesting finding, the regional cessation of copper mining emissions seems to occur around 5,300 years ago. This is a really peculiar finding to me. If you look at paleoclimate records, so records of climate change from lake cores in the region, this seems to coincide with a major Middle Holocene drought that potentially could have dried out inland lakes. And I was just talking to another archaeologist here that mentioned this. This raises the possibility the ancient copper people, or the tradition, the decline might have been related to climate change in the Middle Holocene. So here's the record again. Here's when we find the drought. So thank you. That's all I have, and I want to just thank my advisor, Mark Abbott, Dan Bain, and my funding sources, along with people that helped me in the lab. If you have any questions, let me know. That's it. Yes?
Just a not so, and they couldn't build fires in there against the rock.
Yeah, but they might have removed the mass and worked it near the
I just think
surface.
you're gonna, you know, burning a whole bunch of wood in order to get them out of the pits in the Cargill Cove is different from mining in some places on the.
Yeah, that's a very good point, and I think that also explains why Minong Ridge and McCargo Cove, that pollution there is huge.
Yeah, I think
Um,
that's what came to mind.
Yeah, and it also has the most amount of copper in it. And remember, copper has a really high melting point relative to lead and potassium. Potassium I didn't mention much, but potassium is the #1 metal found in wood smoke. And it's always associated with the lead. So I think this is providing the mechanism. I talk about this in my dissertation. I didn't have time today. But I think when you're working the copper, the impurities are being driven off, like in a process like Buck and Larry were talking about. And they're sticking to wood smoke and then being emitted into the air, and they're settling out into the lakes. So, yeah, differences in the working of the metal, the temperature, the purity of the ore, where it's at, all are going to make a difference. And then that also explains why you see these spatial patterns. So as you're moving the mining, the more distal lakes aren't getting this input, only the close by ones. And so you're actually able to just see these plumes moving.
Cove and went inland.
Dave, is your research and thesis available online?
Not right now. It'll be available in 5 years because I had to put a 5-year hold on it because I'm working on publishing. I have 2 papers out that if you just Google my name and stuff, you can, or go on Google Scholar, you should be able to get a hold of it, or I don't know, my ResearchGate profile, they're online too. Oh yeah, Larry put them on the Facebook copper site too. But I'm working on another publication that is actually going to publish these maps that I showed today with a little bit more description that's not so rushed. Seth?
Over why we just don't see that in the sediment record.
Yeah, it bothers me a lot, and when I first started this research, I went into it with like a European mind state. I was like, agriculture emerged in America in 2000, about 2,000 years ago with maize. Then we're going to see specialists in copper metalworking and mining, and so we're going to see this huge increase in the woodland, but it didn't happen. So yeah, it's confusing, but I think the way to explain it is potentially that the archaic period, the mining was much more intense for whatever reason. The woodland might have been just float copper working, picking up scraps from the past, just maybe not as intensive enough. That's my only explanation.
I don't think there's much for legal artifacts, certainly not the mass of artifacts. Out of copper.
We've got a lot of woodland stuff.
I mean the copper, or
Copper,
copper and
same with the Keelan. You know, so many of the collections that are massed around this area come from woodland.
Susan Martin published one date from the Keweenaw that's from the woodland. That was associated with copper. There's definitely,
From woodland up to archaic.
yeah, it's 20 KE20, it's dated to like 1,500 years ago to 9,000. And it's a pretty big site, but I really don't have any other, I don't really know. So,
Yeah, I mean, it definitely is, it drops off, for sure.
yeah.
I mean, Minong is just huge.
And it seems to correspond with the dates at the mine pits too, on Minong Ridge, like we were talking about. So that's like a piece of evidence that maybe those actual pits are pretty old, but there might have been,
Of the ones they sampled.
yeah, or the ones they sampled. And that also highlights the complete lack of data we have. I mean, just sparse. I mean, people just don't want to fund this stuff. I don't understand it. It's a fantastic, and I talked to Seth, the Royal archaeologist, and he's been working on getting funding. But yeah, there's just a lot of work to be done. There's not much known. This stuff is going to change as we get more data. So I guess that's why we're here today.
I respect that your inquiry into sediment. some years ago, I read the Greenland ice cap ages sort of like tree rings,
Yeah.
and that there was quite a bit of copper pollution shown.
Oh, yeah.
Ring sets that were near the copper age, the bronze age.
Starting as early about 3,500 years ago, you can see lead in the Greenland ice core start to rise above background levels. So it's not as, I think that's the end of the Bronze Age. We think, and that's Hong, like 1995, hits in city thinks it was Greek metalworking. Then you just see it just take off during Roman times. Because the Romans were just, their metalworking was unrivaled until after the Dark Ages.
Do we realize just how strong that has to be for the pollution to occur?
From Italy
Pretty populated.
to all the way to the whole northern hemisphere was contaminated. That shows you how sensitive the environment is to the metal pollution, and in lead in particular, because lead does not cycle naturally in the environment. It's a toxic metal. It just remains very low. It's just, it's not like if you talk about like calcium is picked up by trees, it goes to the leaves blow away, it's a nutrient, so it's constantly moving around. Lead's just not, it's not the same case.
Cross-reference this beginning in the sediment to see where else we can.
It'd be a great idea.
We'll get there.
Yes, sir.
Really interesting work, David. I'm wondering if you've considered the relative amount of lead that would be present from working copper itself as compared to lead that's present in burning of wood and bark.
So they're published. EPA does work on wood smoke because they're interested in it and its effect on respiratory systems. There is a bit of lead in wood smoke. It's a very small amount. In the copper rock, I've actually personally measured a few chunks from Minong Ridge, and it's about 10 parts per million, which is consistent with what we saw in the sediment. The sediment only goes up 5 to 10 part per million. So it's still a very small increase. It's not necessarily toxic, but it's significantly detectable using the analytical equipment we have today. So we can say for certain that the error on our measurements is less than a part per billion. So to kind of get to your question, I think there's going to be a way to tease out how much was wood smoke and how much was copper. But there's just so many variables that are unknown with the copper ore, like how much impurity was associated with that copper, how many, some copper is really pure, some of it has a lot of extra minerals, what kind of technology, what was the rate of working it. So it's hard to back out like how much copper would need to be worked to cause this increase in the lake sediment.
And the other reason I asked is because in working with copper, there's a relatively small amount of lead there, and most of that's going to be on the surface that's released, as opposed to wood, which is burned, you're just released virtually all of it.
Yeah, you're right. Almost something like 95% of the mass of wood is rendered to the air if you get it up to like 1200 degrees. The rest of it's left is potash, which is just like salts that are on the ground. So if you think about if you burn a tree that's 20,000 pounds, you're putting up something like 19,000 pounds of particulates in the air. This is real mass that adds up in lakes. You don't see it. And I started doing like little experiments, like I'd be canoeing and on a lake, and all of a sudden you just catch wind of this little bit of smoke. And you look across the lake a few kilometers away, and all of a sudden you see this little fire. That's showing you that particulates from that fire are reaching your nose. And they're falling in, that adds up if you do that for millennia into the lake sediment. It's not necessarily bad for the lake. So, taking aside that whole question, but it's detectable, and it really makes a difference. So, yes?
How deep is sediment?
Between 3 to 5 meters. So that would be, convert that to feet, 6 to 10 feet of a core, and that would represent about 10,000 years in the sediments. Yeah, we go down to basically hit gravel from the glaciers. The differences in the sediment rates have to do with like the lake's productivity, how deep it is, how big the catchment is. A bigger catchment's going to derive more sediment to the lake, and other things like that. Any other questions? Oh, one more? Well, I'll talk to you later. Thanks. Thank you very much.